Hello, this is Professor Doug. We are now in Chapter 9 of Hibbler Mechanics of Materials, which deals with stress transformation and stress elements in different orientations. So we're going to again look at a number of problems in Excel, and we're going to start with a worksheet in Excel that allows input to generate Mohrs circle. Mohrs circle is a very graphical, visual way to identify planes of principal stress and shear stress. So let's get started. So here's an example. It's not from Hibbler, but it is very useful in illustrating how we can utilize Excel to solve all of these algebraic and trig function equations. Here's the stress element shown at the bottom, and we have sigma x is 2 ksi, that's positive, and the convention is positive as outwards along the x-axis. Sigma y is 3 ksi, also positive, and tau xy, shear stress, is positive at 4 ksi. So essentially, it's 2, 3, 4 ksi are the inputs in what we'll enter into a spreadsheet, but it can be done manually using these trig functions and algebraic equations, and it's a little tedious to do this, so it can be checked by hand, but we already have our answers and solutions, so we're just going to plug into the equation here 2, 3, and 4, and you can see this spreadsheet will draw Mohrs circle for us. And when we look at this, we can open up our problem set and display it alongside the Mohrs circle solution. It might be a little bit hard to see that, so I think I'm going to have to minimize it. And we'll do our best here, right? So let's look at the solutions first. So if we work the problem by hand using a calculator, we get sigma max and sigma min down at the bottom as 6.53 ksi and minus 1.3 ksi. And that would be this orientation that you see up here on the upper right. So here's our solution. On line 6 of the Excel sheet, we have 6.53. Line 7, sigma min, we have minus 1.53. So these are calculated. And it also calculates tau max. So we'll get into that calculation on the next slide. But it importantly will calculate theta p for you and in the orientation of Mohrs circle. And we'll talk about that in a few minutes, theta p. We have minus 41.43 degrees. So that's the principal angle of normal stress. And you can see here theta s is also given. So we have that minus 41.4 down here on the slide. If we add 90 degrees to that, let's see if we can look that on the calculator, 41.4 minus plus 90, that'll get us to 48.6. So that's the other theta p solution. So we want to note this, okay? And then we want to go to the next slide, which will give us the shear stress orientation. So the maximum shear stress is theta sub s, not theta sub p. And that's calculated as shown here. So here it is in our spreadsheet on line 10, row 10, 3.56 degrees. And the tau max calculation is shown here as 4.03 ksi, so that's given on line 8, row 8 of this Excel sheet. And this sigma prime tends to be the center of the circle, right? Based on the calculation, it's basically the average of the x and y sigmas. So you're taking 2 plus 3 and dividing by 2, 2.5. That's the center of the circle and how we draw Mohrs circle. So what does Mohrs circle look like for this particular solution, this problem? Looks like this. Now this convention has tau positive above the x-axis and tau negative, that's the y-axis, tau below the x-axis. You know, typically that convention is opposite and reversed, so this sheet actually is not completely accurate in its depiction, but the idea is if you look at sigma max, that would be this right component of the circle here, 6.53, and sigma min would be on the left side here along the tau axis, right? And that would be minus 1.53. The center of the circle would be here. We said it was 2.5, right? So you can read it 2.5, that's on the tau axis. Here's 2, here's 4, 3 would be in the middle. It's about halfway between 2 and 3. And then the radius of the circle is important, because the radius of the circle is tau max. And so you can see it right here that wherever we draw the radius, you will end up with a radius of 4.03. So just a little bit above 4 for a radius. And then we have -4 in the other orientation. So the angles theta p, theta s, we'll get into that in the next example. So let's drag in another examples. And you can see the notation here is Mohrs circles in blue. The original stress state is in red, and the principal stress planes along this axis here are shown. We said sigma max and sigma min. There they are over in this block here with the circle center. So let's look at this problem. And this is from Hibbeler. And we're going to change our inputs. So sigma x is now -100 into compression into the element. And then there is no sigma y, it's 0, so that's given. I'm looking right up here, my friends, right? And tau xy is positive 25. So you can see Mohrs circle is changing in its dimensions. So here is our Mohrs circle for this orientation. All right, so the rotated element, right? Principal planes of in-plane principal stresses now are -106, that's this, it's rounded, and 5.90. So we have sigma max and sigma min. So 5.90, that would be this point on Mohrs circle over here, and sigma min would be over here, and those are given here, and it checks out with our solutions. It's sigma 1 and sigma 2 in this example, right? So sigma 1 is actually sigma max, and sigma 2 is sigma min, right? So the orientation of the principal plane we calculated with our spreadsheet, and you can see there's trig functions in here, -13.28. And then again, if we add 90 degrees to that, we get 76.72. So these are the solutions. We are then substituting that into this equation here to come up with the -106. So the answer is -13.3, and you can see that down from the horizontal here, right? Yes. Okay, so this angle, if we were able to draw it in green, from the center of the circle to sigma max down to this radius point here, that angle would be 13.3 below the x-axis, so it's minus. All right, so there it is. Then we want to know what's the maximum in-plane shear stress and the principal angle of that shear stress, and we get 55.9 using these trig functions down here. There it is calculated for us on row 8, and that angle would be 31.71, so that's shown in the center diagram here, the in-plane, maximum in-plane shear stress and its principal angle. So that's what we need to calculate for this type of problem solution. Our second example is interesting, and this comes from the field of rock mechanics and structural geology. I'm actually a geologist as well, and so this is something that I found in one of my geology magazines. I think it's The Professional Geologist from AIPG, and they posed this question for readers of the magazine. It says, in our studies of rock mechanics and structural geology, we deal with the concepts of the stress vector, force per unit area on a point on a plane, and the stress tensor, which is the definition of the overall state of stress. Find the stress vector, S, if the unit normal vector for the plane, N, and the stress tensor are given. So you got all these, a matrix T for the stress tensor, 3 by 3 matrix, and then you have a vector, N, X, Y, Z. And what you need to do here is to find the stress tensor, you're going to do matrix multiplication. So it's rather simple. So we're just going to actually empty this matrix out, clear it out. And right now we know that we put our plane vector, it's not a vector, it is a vector, -2/3, I'm sorry, X, Y, Z. So we take it right off of equation 1. -2/3 X, I keep saying minus, it's positive. Positive 2/3 S, X, -2/3 Y, positive 1/3 Z. So you can have Excel convert these to a fraction, right here, all right? And that's the best way to show it. Now the stress tensor, let's look at the actual element, right? It's in 3 dimensions, X, Y, Y is out, and Z is up, okay? X is to the right. and left. So we want to fill in the blanks of the stress tensor that you see here. So we're going to look at the X face here, which is in blue. So we've got 7. We have none in the Y orientation, and then we have tau xz of -2. That's it. I have them color-coded. Then on the Y face, which is in green, we have nothing in the X orientation, XY. We have 5 in the YY, and I'm reading the vectors here on the face. And then we have nothing for tau XY or YX. And then the last one, we have the top face is Z, upwards. We have -2 for tau, we have nothing for y, and then we have 4 for ZZ, the red arrow vector. So that's it. So now, what do we do with these, right? You take this stress tensor, which is this, and we looked at our element, you multiply by the vector, the plane vector, which is a 3 by 1. So you're entering matrix A in this cell block, 3 by 3. You're entering vector B in this column, and then you're selecting a range, an output range, and my output range is just this column over here, M 17 through 19. And then in the formula bar over here, you're just typing matrix multiplication, M mult, and you're multiplying the G17 through I19, that's this 3 by 3 matrix, by the vector K17 to K19, the column vector, and then just hit enter, and it'll populate the other 2 cells. You can see they're grayed out. So that's it. Now the answer is 4 minus 3.330. What does this look like graphically? For that, I went to MATLAB because it can plot 3D vectors very nicely. So you can have the unit normal vector is here. This is the plane vector, and you can see its orientation at 2/3 x minus 2/3 y and 1/3 z. So you can look at that, and it's in space, in 3D space. And then we have our stress vector, which was the solution of the matrix multiplication of the stress tensor times the plane vector. All right, and that's the stress tensor in the xy plane only. There's no z component, it's 0. So we have 4x, you can see the tip of the arrow, and then minus 3.33, 3 1/3 y negative, and that would be this. So there's no z component to that. So here you have it in 3 dimensions plotted and performing matrix multiplications. You don't have to do matrix inverse, which we did in chapter 4, module 4, but I do want to have a lot of visuals in this particular example to show, what this stress tensor looks like in 3 dimensions, and what the stress vector and normal vector look like also plotted in 3 dimensions.